And of course, like here now, I try to tell you everything about data efficiency that was not told in the previous ones. But in the end, actually, I'm going to like recap many of the things that already were presented by all three speakers before me. So we talk about AI, but actually most of the things that have been tackled now here by the three speakers in the session before me have been more about like learning-based things, which is of course natural, because if we talk about data efficiency, there's the element of data. And then of course, if we have data, we want to learn something. And not all AI is learning-based. So basically machine learning, we scale down from the grand challenges of making like human-like, real AI, to more practical things, where we think of that can machines do what we, as thinking entities, can do. Which means adapt observations, learn from past experience, or understand things, as we thinking entities would do. So kind of practical things, which is of course like quite well aligned with industrial applications as well. We don't want to do things that save time, add robustness, help us human operators. And of course, like you've probably been following social media and watching TV and so on, so you know that AI or machine learning can already do impressive things. Say, grasp concepts like style in art, or generate realistic content, such as human faces, or even like mix different faces of humans. So all these people don't exist. They are imagined by a deep neural network model, basically. And the same applies for, let's see, displays. Generate things like animals and interpolate between animal images. And like this would fool me, even though I love cats and dogs, so I know them quite well, but this is quite impressive. And then like generate contents from prompt, like an armchair in the shape of an avocado. Something like that would probably not exist, but the AI which has been trained with a lot of images and a lot of text can then combine these things and kind of interpolate in the space of things to come up with a chair that looks like an avocado. Well, impressive, perhaps not that useful. But then, of course, like for machines, like understanding scenes, tracking, training RL agents, these are actually like going the realm of practical things. There is a snake in paradise, though. Typically, these models are very data hungry. That's why we have this session here, data efficiency. And the models become quite bloated, so you need a lot of compute to actually like handle these models. Well, a problem perhaps. If we talk about like deep neural networks, which were actually mentioned in one of the questions already, and which also Simo brought up just a moment ago, these models are hard to interpret. Not impossible, but near impossible. Like, what did they actually learn? What did they not learn? Hard to say. And they might be sneaky in a way, that they might be actually quite sensitive to the details of the inputs, which you then perhaps doesn't know. So for example, these images here, like this is apparently a king penguin, according to the model. This image is a starfish, this is a baseball, and this is an electric guitar. So something in the image triggers a nerve kind of in the model that makes it think that that's a baseball, so on. And then if we really have these things operating, things in harbor, for example, then there are like these safety concerns and things. Or Simo mentioned self-driving cars. We want to be quite certain that these things are not easily foolable on purpose or by mistake. So these are all things that we should and are having an eye on. And even like there's this famous quote that tells that contemporary neural network models are spotty and pointillistic. Well, useful, impressive, but not reliable. So what are the measures that we can take to tackle this? Well, already in the two previous more technical talks, like things regarding robustness and prior knowledge and probabilistic approaches were brought up. So, cats and dogs are good examples. So what the neural network model is basically the same model that Simon just showed you, kind of, that it typically learned to draw a line between classes of inputs. So say you have trained a model with cats and dogs, so the goal is to separate that. Tell that, well, when you then show the model unseen inputs, then it might then figure out that this is probably a cat or this is a dog. The problem typically is that that's the only information that's given to the model. You have a very flexible model which has been trained on cats and dogs. Well, you deploy this model then in the real world, and one day it encounters a horse. It's never seen a horse. What will it do? Or even worse, it encounters a car, which is very far from the training data it's seen. It's only seen cats and dogs. So in its world, there's only cats and dogs. So it will probably then say that, well, the horse is like either a cat or a dog, and even the car is either a cat or a dog. By prior knowledge, that was just discussed, and probabilistic methods, we might want to input some further prior knowledge here, which might not be prior knowledge from physics, but more of like kind of inductive biases that we want to bias the model towards. To say, for example, that, well, if you see something that you haven't seen in the training phase, don't be certain about that. So here, the uncertainty of the model predictions are depicted by like the lightness of the color. So for example, now it would still say that the horse and the car are dogs, but it will also signal that I'm super uncertain about this. Don't trust me on this. And this is more of the kind of uncertainty that we would like the models to output. So, how do we get there? Well, this is sort of like combination of course, these extremely flexible, impressive models, but also then piggybacking on theory from statistics. Basically combining prior knowledge about being uncertain, probabilistic methods, with these deep models which are flexible and can learn from data. And of course then, you cannot learn everything. You cannot observe everything in the world. Then you don't need a machine learning model. You need a good database. So basically, also then, there are these gaps in the data. Even though you would have observed a lot of data, there's always gaps, or things that you don't account for when you build your model and collect the data. So that's why actually specifying the things that you know, for example, from common sense or physics, and also the things that you don't know, putting that into the model. That I don't know if my data set that I collected was representative enough. So please be uncertain of the things that were not in the training data. This is kind of the knowledge that we would pass to the model in the best case. Of course, like many of these, like application-wise, many of these things were already like covered in the previous presentations. So here's just like an image example of, well, if you have trained your model on this is CIFAR 10, which is a common benchmark data set, then if you test on some different types of data, like images still, but which are sort of like different from the ones that you trained on, you would like the model to signal that like these data points look like the ones I was trained on, but these data points are kind of different. I don't really know about this. So like that's what I try to depict here, like most similar, least similar to the training set, basically. And then if you have something totally different, like then it should still try to do decisions, but then be even more uncertain. And that's like this totally different data set, is this bump here. So it's clearly more uncertain about that. Well, where is these things useful? Well, knowledge transfer, domain adaptation. That was actually very well covered in Ville's presentation earlier. So basically, you might have a model trained on some hardware, some environment, some setting, some customer's data or something, and then you want it to generalize to some case where it has not been like it hasn't seen that use case, has seen that hardware, has seen that customer, that port, or so. You want to generalize. This is nice because then you don't need to collect excessive amounts of data. You can kind of reuse the knowledge that the model already has. Or then, well, it also links to robustness. The real world is chaotic. It's ugly. It's not like in simulators where things work the way we want. It's clean. We can do augmentations in simulations, but there's always something that we don't cover. Suddenly there's a rabbit jumping in front of us. And we want to do methods that are robust to the ugliness and the real world. And then, of course, like Will already covered RL, but one point there was that like training on real hardware is challenging because it might break the hardware, it might take a lot of time. So then, by having like probabilistic approaches, then might help us reuse the knowledge more efficiently, which reduces the training time. So this is an open source robot that learns to walk. Our current best time is in 8 minutes, which is actually quite good. It's 8 minutes of not simulator time, but actually 8 minutes of the robot just trying its legs, how they work, and then learning to walk. So, to recap, contemporary AI and machine learning can do complicated and impressive things. But generalization, actually sort of adapting to things that it hasn't seen, is still a bit shaky. And to make these things actually scalable, useful, to reduce the need for excessive amounts of data, because we want things to work here in the ugly real world. That are things that are being tackled right now. So for models to know what they are uncertain of, and also better leverage things that they actually are certain of, that they know well. I think that is fascinating. Great. That concludes my presentation.